In section 2.4, we talk about chain rules for information measures. First, we have the chain rule for entropy, which says that the entropy of x1, x2 up to xn is equal to the summation from I equals 1 to n, entropy of xi conditioning on x1, x2 up to xi minus 1. As an illustration, we look at some examples. First, for n equals 2, the chain rule says that the entropy of x1, x2 is equal to the entropy of x1 plus the entropy of x2 given x1. This is just proposition 2.6 that we have seen before. For n equals 3, it says that the entropy of x1, x2, x3 is equal to the entropy of x1 plus the entropy of x2 conditioning on x1 plus the entropy of x3 conditioning on x1 and x2. And then we have the chain rule for conditional entropy, which is exactly the same as the chain rule for entropy, except that we are now conditioning on a random variable y. We also have the chain rule for mutual information, which says that the mutual information between x1, x2 all the way up to xn and y is equal to summation I from 1 up to n, the mutual information between xi and y conditioning on x1, x2 up to xi minus 1. As an illustration, we look at some examples. For n equals 2, the chain rule says that the mutual information between 1, 2, and y is equal to the mutual information between 1 and y plus the mutual information between 2 and y given 1. For n equals 3, the chain rule says that the mutual information between 1, 2, and 3 given y is equal to the mutual information between 1 and y plus the mutual information between 2 and y given 1 plus the mutual information between 3 and y given 1 and 2. Then we also have the chain rule for conditional mutual information, which is exactly the same as the chain rule for mutual information, except that we now condition on a random variable z. We now prove the chain rule for conditional entropy. First, consider conditional entropy of x1, x2 up to xn given y is equal to entropy of x1, x2 up to xn and y minus entropy of y. This is just to apply the chain rule in reverse. Now we combine the random variables x1 and y to obtain entropy of x1, y as a pair, x2 all the way up to xn minus entropy of y. Then we apply chain rule to obtain entropy of x1, y plus summation I equals 2 up to n, entropy of xi, conditioning on x1y, x2, all the way up to xi minus 1, and then minus entropy of y. And then we move y to the end of the conditioning. Now entropy of x1y minus entropy of y is equal to entropy of x1 given y. So we see that entropy of x1 given y is actually the first term in the summation. By combining these two terms, we can finally write summation I from 1 up to n, entropy of xi conditioning on x1, x2 up to xi minus 1, and y. Now offer an alternative proof of proposition 2.25, which gives different insights. First, conditional entropy of x1, x2 up to xn given y can be written as summation y py times entropy of x1, x2 up to xn conditioning on a particular y. Because we are conditioning on a particular y, we actually can apply the unconditional version of the chain rule to obtain summation I equals 1 up to n entropy of xi given x1, x2 up to xi minus 1 and a particular y. Now we switch the order of the summation which can be justified to obtain summation I equals 1 up to n, summation y, py, entropy of xi given x1, x2 up to xi minus 1, and a particular y. Now the inner sum is just the conditional entropy of xi given x1 up to xi minus 1 and y, and so we have proved proposition 2.25. This alternative proof explains why proposition 2.25, namely the conditional version of the chain rule, can be obtained from proposition 2.24, namely the unconditional version of the chain rule, by conditioning on y throughout the formula.